Welcome back to CS520. In this session I'm going to talk about POSIX threads, threads libraries that can be used with C. I'm going to do it by looking at a series of examples, and I'm going to use the same pi algorithm that we talked about earlier in the course. So it's this numeric integration where we're going to compute the area of these rectangles in order to estimate the area under this curve. This is actually a good program for threads because we can perhaps improve the performance of the program by computing the area of rectangles at the same time. So I can divide these rectangles up, hand groups of them off to different threads, and the threads can be computing the areas at the same time. And we should, hopefully, if we have more than one processor that on a machine we're running on, we should see better performance. Okay. So let's start out by looking at a C program for this algorithm. Again, it's going to look similar to the Java program we looked at earlier. I call this program this serial program pi0.c. All these programs I'm talking about in this session are available on Agate in ~CS520 public pi-POSIX. And this is just a simple C program. It defines how many intervals we need to have to get the precision that we need. And it just loops over that many intervals, evaluates the function at the midpoint of the interval, sums all those up, all those function values up, and then on the outside of the loop it actually multiplies by the width, because remember the area of the interval is the width times the function value. This is has just factored the multiplication out of the loop and just does one multiplication in order to, again, to improve performance. These programs, I have a simple timer mechanism in here to start a timer and stop a timer, and then we can, when we stop the timer, it will actually print out how much time was consumed, and I'm talking about clock time. And then finally, it'll print out an estimation of pi. Okay, so just the basic algorithm there written in serial C. Okay, let's look at a series of programs that uses threads to do this. This one I call pi4.c. Again, I have a variety of versions of this program. In this version, I'll create a set of children threads, because in C you get one thread for free. Remember, that's just a basic C program. You get one thread for free. But in POSIX Threads, I have an ability to create additional threads. So I'll create a set of threads. They'll all be given a set of intervals to operate on. They'll compute a partial sum. They're going to store the partial sum in a global array, where the array is shared by all the threads. Remember, the threads are going to share global variables, but each thread will have its own stack, so the local variables will be their own distinct copy. Okay, so the children threads will compute a partial sum. In other words, the sum of function values for the intervals they were assigned. They'll put their partial sum into an array slot, where the slot is particular to the thread. So we make sure we don't have any conflicts. No threads are going to be touching the same element of the array. Then we'll use a POSIX primitive called join. So the main thread knows when all the other children threads are done, and the main thread can then sum the partial values into a global sum and print it out. Okay, so let's start looking at some of the POSIX stuff in here. First of all, you'll notice I really should start with the header file. Right, in order to use POSIX threads, I'm going to have to include pthread.h. I also have a few other header files here to allow me to do better error messages if I get a system error out of one of these pthread routines. Okay, then I declare an array of this pthread_t type, which is basically I think of it as a thread ID. Right? When I create a thread, I get back a handle that allows me to manipulate that thread. These arrays I'm going to use have a maximum number of threads I can support. In this case, I've got it set to 24. Second thing is I have this partial sums array that I mentioned. Every thread will be given an element of this array where they'll store their partial sum. And when they're all done, then the main thread will run through, sum up the partial sums in this array to get the final sum. I have to allocate intervals to threads, so I actually work at it fairly hard here to try to get them as even as possible, because one thing, if you're worried about performance, if you don't spread the workload evenly among the threads, it'll limit your performance. I'm probably a little bit too obsessive here. I'm not going to go over the details of how I do this. You can look at the code later. Take a closer look at that. Okay, so main starts up. I get one thread for free. It's like a normal C program. I'm reading the number of threads I want to use from the command line. I go ahead and start the timer. I do some calculations to figure out which thread is going to do which set of intervals. And then I actually have a loop to create the number of threads I want. There's a primitive called pthread_create. Again, there's man pages for all these pthread routines, as well as, I'm sure if you Google around you'll see lots of documentation for pthreads. But there's a function that I can call to create a thread. The first parameter is an output parameter where the system will put the thread ID, the thread handle that I can use later to manipulate the thread. There's a second parameter that allows me to assign characteristics to the thread. I'm just using the defaults here, so I'm not doing anything fancy. Don't really want to get into all that either. We're just going to use the defaults in this class. Okay, then the third parameter is actually a function pointer. So it's a function pointer. So C provides pointers to functions also, as well as pointers to data. And this is I call it the work function. This is what the thread is being created to do. It's going to execute this function, and when this function returns, the thread will terminate. Okay. Then the work function has a prototype. I should have gone back and pointed it out here. The work function has to have this prototype. Right? It takes one void star and it returns a void star. I am using this fourth parameter to thread create is the void star that will be passed as a parameter. And you can see I'm being shameless again. I'm doing my same old trick that I told you I shouldn't really do, but I'm putting an integer in that void star. And what is it? It's simply the for loop control variable, right? So I'm telling each thread, I'm giving it an ID in the range 0 to n-1. That allows the thread to know which work it should do. The thread 0 will do the first work closer to the point 0 on the x-axis, and the thread n-1 will do the interval that ends at 1 on the right end of the interval that we're computing the area of under the curve. So by passing into each thread a thread ID, they know what to do, what piece of the work to do. In general, though, you can pass in a struct here, a pointer to a struct or something, and pass a lot of information into the thread as it starts up. So this will create a thread. A thread will start running concurrently if we have more than one processor. What's the main thread to go on to do then? Well, it initializes the global sum, which is just a local variable now inside of main. Then it has another for loop where it waits for the threads to finish. And this pthread join function, the thread who calls it waits until the thread given by the first parameter. Again, this is a thread ID or a thread handle. pthread join makes the caller wait until that thread finishes. Obviously there's some options that I could choose. Again, I'm just using the defaults here. I think what this one actually does, it would give me the return status of that thread. I don't really care about that in this case. Okay. Notice again, I'm using this error function. Whenever I call pthread routines, again, you should check for failure. As always, on any library routine you call, you should check for failure. Things can go wrong. Let's go look at my error routine real quick. I think, unfortunately, it spreads across 2 pages of this printout. So down here, here's my error routine. I'm able to pass it a string. And then it uses a p-error function, which is a library routine, which will examine and provide more information about the error that just occurred, the last error that occurred in a C library routine. And the next thing it does after that then is it exits the program. So I consider these all to be fatal errors in this program. Okay. So main is going to start the threads and wait for each one of them to finish. When they're all finished, when an individual thread is finished, the ith thread is finished, then I pick up the partial sum for I and sum it to my global sum, and go wait for the next thread. When they're all finished, I'll exit this loop, and then I can do that final multiply. This is the width, by the way, of the interval. Right? I've divided the interval 0 to 1 by this many number of subintervals. So that's the width of an interval. I'm just doing that final multiplication to get the value of pi. And I stop the timer and print the result. All right, let's look at the work function now. Remember, this is what each thread is going to do. So it starts up and it has to do some arithmetic here to figure out what its intervals are, where it's starting. The low is the first interval it's going to do, and high is the first interval it's not going to do. So it's running a for loop over those intervals from low up to, but not including high. And it's doing the same old pi computation. It evaluates the function at that point and now sums it to a local sum. Local sum, again, it's just a local variable, so it's not in a shared memory location. So we don't have to worry about that, about conflicts. And then when I get done, I have a local sum. I stash it in the global array, but in a unique location given by my thread ID, my logical thread ID. So I know I'm the only one writing there, so that's safe too. I don't have to worry about a conflict there. So very simple program. I can just use thread join to tell me when the threads are done. I've carefully orchestrated it so threads cannot possibly interfere, so I don't need any locking. And it's simple enough, I don't need any condition variables either, any waiting or signaling. All right. So what if I run that program? What kind of performance do I get? And here's what happened when I ran this program. These two programs, the serial program and this Pi3 program. And also I get similar results for my other two versions that I'll talk about later. But I run it on my desktop. The serial program, it takes about 0.330 seconds to run. If I run my parallel program, my threaded program, with one thread, so it's just the master thread, starts up one child and waits for that child, so the child is just doing all the work essentially. It's the same time, and that's pretty much what we'd expect. There's a little bit of overhead to creating the threads and doing the thread joins, but it's not much. You don't even notice that the time of the computation is dominated by doing the pi calculation. So we would expect these to be about the same, and they are. As I up the number of threads, though, I see a performance improvement for a while. Right? I use 2 children threads. Now I divide the work in half, and the running time is a little bit slower than half the running time. Again, indicating there's a little bit of overhead to starting and coordinating these threads. I go to 4 threads, and again I see a performance improvement, but a little bit less than 1/2, because again there's some overhead to using threads. When I get to 8 threads, though, I don't see a performance improvement anymore. go to 16 threads, I don't see a performance improvement anymore. So what can we conclude from this actually? Think about that for a moment. Can we say anything about the number of threads we have? Well, yeah, we must be, there must be, it's not the number, I'm sorry. Can we say anything about the number of CPUs we're on the machine we're running on? And yeah, I think this is pretty good evidence that there must be 4 CPUs on the machine I am running on. So this illustrates that threads can help you leverage the hardware you've got. It can let you divide up your computation into sub-computations and assign those sub-computations to different CPUs and actually see performance improvement in terms of the clock time, the actual real time. And again, I'm going to look at some other versions of the program, but the performance results are all about the same for all the parallel programs. So let's look at it. Look at another version. What's the story on this version? Well, this version is meant to illustrate the use of mutexes or locks in POSIX Threads. So rather than using an array so that we're careful that the local partial sums are written to a unique spot for each thread, I'm going to use a lock to protect the global sum that each thread is going to add in its partial sum to. And then I'll use thread join to terminate, to know when the threads are terminating. Okay, a lot of this is the same, except now, let me use a different color here. Except now we have a mutex type. So this is a little pthread object, and I declare, and then I'm able to lock it, and that provides this mutual exclusion. It allows me to protect critical sections in the code. The rest of the code is pretty much the same. Again, one difference, however, is I've got to initialize that mutex. So I pass in the address of the object so that the system can initialize that blob, that struct, or whatever it is under the surface there, whatever it is that this pthread mutex type is. Right? I pass in the address and I initialize that. Again, I'm just using default characteristics for the mutex. As before, I do a pthread create, and the main thread does a pthread join to shut them down. At this point, though, when the threads are done, I have a global sum, and I don't have to go through an array and gather the partial sums. The individual threads have added their own sum safely to the global sum, so I can just do the multiplication by the width, stop the timer, and print the answer again. Okay, if we look at the work function here, it's the same. We calculate what work we need to do. We calculate the local sum using our intervals. But then, once we have our local sum, we have to use the mutex in order to safely add our partial sum to the global sum. So at this point now, we do a lock. We do a mutex lock on that initialized mutex. Once we got that lock, we know we're the only one running, and we can safely do this addition to the global sum. Remember, the way these locks work is that you will, if you can't get the lock, you'll be blocked. You'll wait until somebody gives up the lock and you obtain it. So you grab the lock, you can safely do the update to the global variable, and then you do an unlock. Okay. Again, very simple, but illustrating how you can use mutexes to make sure you can safely update a shared variable. All right. The last program is more convoluted because I want to illustrate now condition variables as well as mutexes. So this program is not going to use it's not going to use the thread join. I'm going to use condition variables to identify when all the threads are done. Okay, so I look through here again. I've got my pthread array for the thread IDs. I have a mutex again, so I can safely do my update. But now I have a pthread condition variable too. Declare that. Again, it's in shared memory because it's being shared. These mutexes and condition variables are being shared by all the threads, so I need to put it in global memory. Go into the main. The main thread will initialize the mutex just like in the last program. But now it'll also initialize a condition variable. Same concept. I pass the address of the condition variable. I don't care about the characteristics. I use the defaults again. Main thread then, like before, it creates a set of threads. The difference is now this program is more convoluted. Thread 0 is doing some work. So what do I mean by that? I mean the main thread is doing some of the work. This is a little bit tricky. So it creates the threads. Remember, the threads are all doing work, being passed something. But now the for loop here, I'm only creating n-1 threads now, with the thread IDs running from 1 to n-1, because the main thread is going to do the work for child 0, essentially, as if it was child 0. So main thread goes off, does some of the work. Then it comes back and it needs to check, am I done? So there's a global count variable here that's keeping track of children threads as they exit. So we want to know when n-1 of them have exited. And I guess we actually want to know n because the main thread itself is going to count off. So we come in, we bump that count up, and we check to see if it's in. Now, if it's not in, we have to wait for all the children to finish. So this is where we do a pthread condition wait. And notice again, as I talked about in the generic case, the wait takes a condition variable and a mutex, and when the caller calls wait, it has to own that mutex. I'm going to have to explain to you in a minute how that happens. The main thread gets the mutex down below in the work function. That's the tricky part of this program. But the idea about wait is wait has to have a condition variable it's waiting on, and then there has to be an associated mutex that the caller has locked. And this means I'll wait for somebody to signal me. The last thread that finishes will signal me, which will allow me to wake up. I'll do the multiplication by width, stop the timer, and print the result. All right, let's take a look at this work function. Again, it's the same as before. We figure out what work we're doing, and we do our local sum. Then, before we update the global sum, we grab the mutex lock. So we grab the lock. That means we can safely update the global sum. And then the code gets tricky. Here, if the ID is 0, that means I'm the main thread. Right, the main thread, or what do I call the parent in this comment. On the main thread, I just return. So notice though, tricky code here. Main thread's doing this, the work for ID 0. It locks, it updates the global sum, and then it just returns. So when it returns, it's holding the lock. It's holding the lock, and that's what makes this code that we were looking at before up here work, right? I do work 0. When I return, I still hold the lock. So when I do this condition wait, I hold the lock, which is what I need to be doing when I do a wait. So the program is a little bit tricky. If I'm not the main thread, though, I bump the counter to see if I'm last. If I'm the last one, if I'm the nth thread to finish, the last thread to finish, then I'm going to do the condition signal because the main thread might be waiting for me to signal that all threads are done. And then I unlock the mutex. I unlock the mutex to allow other people to get access to the shared data. And then I fall out the bottom of this function, which means I return from that function. Okay. So again, just to reiterate what the main thread's doing, it's waiting, it bumps up the counter, and then it waits for everyone to finish. It's waiting for a signal to come. And when it does the final multiplication and prints the result. Now, what if the main thread is last? If the main thread is last to finish, it comes in here, realizes that it ups the count, and it must be equal to n. It doesn't do any of this. There's no need to wait then. Everyone else is done, and I can just fall in here without the wait. So, you know, it illustrates that signals can be sent without any waiters, and the signals just disappear into the ether. Nobody catches them. If there's no waiters, the signal has no effect. Okay. All right, so what I've tried to do here with these examples is just illustrate how the generic thread operations of creating threads, locking locks, obtaining locks, and signal and wait work in the context of POSIX threads. Okay, let's stop here.